Good afternoon, everybody. Welcome to the RISC-V Summit. Great to see so many people, like maybe a double from the previous workshop in Milpitas a year ago. My name is Zvonimir Bandik. I work as a manager in Western Digital Research Organization, part of the CTO office. And I've been focused on memory controller technologies, embedded CPU technologies, interfaces for data center, storage and compute, and more recently on compute accelerators as well. We've been part of RISC-V organization for a long time, and I'll tell some of our projects and some of our interests. So today I'll be talking about CPU project in Western Digital. We'll talk about embedded cores, and we'll talk about the vision for the data center processors with open interfaces. And we'll have three presenters, myself, Robert Goulet, and Dejan Vucinic. Agenda. So we'll start by explaining the enterprise data center vision, which is all about the open interfaces. In particular, what kind of RISC-V cores we would like to see in the future, which is the direction that we are moving into. What kind of memory interfaces and accelerator interfaces we would like, and what kind of cache coherence interface we would like to see. And then we'll describe more details in this presentation. I'll also list our planned open source contributions, and then we'll transition to Robert Goulet giving an overview of the RISC-V Core microarchitecture. And after that, Dan will give a technical overview of the OmniExtend protocol. You have heard about these three topics this morning from Martin Fink, so this is now expansion and kind of providing more details. And I invite everybody to Western Digital booth. We have a OmniExtend demo, and you can also in the booth ask any additional questions, including questions to the RISC-V Core designers. So what is the vision of the RISC-V open architecture data center CPU? So we would like to kind of share what our vision is. And we still see this general purpose CPU being important, but a little bit different than where it is today. So it still needs to be multi-threaded, multi-core CPU. But we believe that there is a reduced pressure on a single thread performance that core needs to deliver. So we kind of see medium performance out of order RISC-V cores for general purpose OS and software applications. We want to have cores powerful enough to run drivers, to enumerate all the peripherals on boot. But we believe that the compute is shifting to the compute accelerators. We think that connectivity is a more important component of the future data center CPU. So we want to see enablement for standardized and open JEDEC interfaces. An example of that would be NVDMP DDR interface for the emerging non-volatile memory standardized in JEDEC. So this is a good example which levels the play, removes the control points, and allows future customers to gain access to a number of different very powerful, low latency, high density memory technologies. Then it's all about the accelerators these days when it comes to compute. So it's very important to enable these accelerators to be able to do a good job. And in order for them to do a good job, they need a high bandwidth and they need a low latency. So this is something that's really required to support machine learning and inference workloads from core to the edge, from the data center to the edge device. And finally, it's not just enough to have a low latency and high bandwidth interfaces. You need to enable smart interfaces. And along those lines, we want to see a support for standardized memory protocol fabric. This is something that we have announced this morning by Martin in his keynote. It's an OmniExtend memory fabric, which is basically extension of a tiling cache coherence protocol over A02.3 physical layer, basically Ethernet 5. And this is something that allows coherent scale-out for the memory-centric applications and enables traditional SMP architectures, which are interesting and convenient because they do not require porting of the software. You can use a lot of legacy software on these types of architectures. So why is OmniExtend important to Western Digital? It's important to us because it enables memory-centric architectures, which is something that is our passion and we started talking about the last 12 months. Basically, as you develop an open cache coherence memory fabric, and as you enable its switching with programmable switches, and in Western Digital we've been prototyping with barefoot network switches, you create a traditional SMP architecture, and you can actually have large number of RISC-V compute nodes being on the same memory domain. Even more interesting, you can actually have CPUs from different manufacturers potentially sitting on the same memory domain, which becomes really exciting and enables some companies to focus on acceleration of compute and enables some companies like Western Digital to focus on things that are interesting for memories. So you can easily envision that with this type of architecture, you can have a standardized and open interfaces for memory appliances that could be based on DRAM or in future on emerging high-density non-volatile memories. And in terms of what our planned open source contributions are, and now with added links as well. So today we have released our Swerve ISS instruction set simulator. The link is Western Digital Corporation on the GitHub. Then for the January of next year, we are planning to release RTL of our two-way superscalar 9-stage Swerve core, and Robert is going to introduce it in a couple of minutes. And our reference implementations for OmniExtend specification and the bitstream are actually already on the GitHub starting today. And this is where we plan over the course of next 6 months to start adding our switch implementation in P4 for the Barefoot Tofino, as well as the board designs that will support OmniExtend and standardized connector compute cards that can connect on this fabric. And we don't know exactly when, but we have an internal project in the CTO office working on a RISC-V firmware development toolchain. And it's our intention that over the time this becomes available as an open source contribution as well. So that's it from me. Next one is Robert. Actually, it's my great pleasure to introduce Robert Goulet. Robert Goulet came to... I only have 10 seconds for this. So Robert Goulet came to Western Digital via a long career in Intel, IBM, Sun, and Oracle, and is a chief architect and a senior fellow in Western Digital, and he leads our RISC-5 Core microarchitecture project.
Okay. Everything you said about me was true, but I've never worked for Intel. I get that caveat out right away. So, I'm Robert Goulet. Today I'll be talking about Swerve Core, which is Western Digital's first RISC-V Core. And the purpose of this core, we were trying to design an in-order core, minimize speculation, and get the highest performance we could for use internally within Western Digital. That was the primary focus. And as already announced, we're going to be open sourcing this course next year. So this is a block diagram of the core, and basically there's broken into two pieces. The blue components are the RISC-V components, and then the gray components are kind of the things that go around the RISC-V components, the non-RISC-V components. So starting with the RISC-V core itself, it's a 32-bit RISC-V implementation. We implement the I, the M, the C extensions. So we enter the integer set, which is around 45, 50 instructions. We do the M, multiply, divide, and we implement the compression extension. So with compression, typically we see about 40, 50% compression. That's typically what was, you find that in the RISC-V reader. We see that same sort of compression. We only have 4 units on this core. It's a very simple, basic core, an instruction fetch unit. We fetch up to 16 bytes per cycle from either an ICCM, closely coupled memory, or an instruction cache. We have a branch prediction in the IFU. We do the alignment of the instructions in the IFU. The other one of the 4 units we have is a decode unit. And in this unit, we decode up to 2 instructions per cycle. We schedule them down the execution pipes for best performance. We handle interrupts, exceptions, and things like that. The execution unit has all of the ALUs, I'll talk to in a minute. It has the multiplier and the divider. And the load store unit is responsible for executing all loads and stores on the core. And so sort of the non-RISC-V components, we have 2 closely coupled memories that are in pipe. One is the D for the data side, and one is I for the instruction side. We have in our current implementation a 4-way set 64-byte instruction cache. And for the closely coupled memories, we support configurable sizes from 4 all the way up to 512K in powers of 2. And for the instruction cache, we support sizes from 16K all the way up to 256K. RISC-V, as it comes, doesn't support vectored interrupts, so we had to come up with a specification to allow us to support up to 255 external interrupts. We support up to 15 priority levels. We support level sensitive, edge sensitive on the inputs. And so we kind of built all that in. It's RISC-V compliant, it all goes to one handler, but we're able to pick between those 255 the highest priority interrupt and present it to the core, and then the core is able to vector directly to the interrupt. Debug, we implement the RISC-V debug standard as it stands today. We currently have that, so you can, through JTAG, you can halt the core, you can read and write CSRs, read and write the GPRs, you can single step, you can read and write our internal memories, and as also part of the spec, we support the system bus port, which is shown here right there as the debug bus master we support. So you can actually, through JTAG, you can actually read and write the platform memory while the core is running. So we implement the RISC-V debug port spec. We're a Harvard bus architecture, so we have a load bus master, we have an instruction bus master, and then we have a slave port on the bus so that the platform can get in and configure both the ICCM and the DCCM, our internal core memories. As of today, we support the 64-bit AXI protocol as well as the HB Lite protocol. AXI is a non-blocking protocol. HB Lite is a blocking protocol. We're doing this in TSMC. The target frequency is 1 gigahertz, and we're running at a slow corner, SSG corner. For the microarchitecture, we're a 9-stage pipe, including write back. We're two, as already mentioned, we're 2 issue in order. I always like to know in every architecture where the thing can stall. So we stall before fetch, we stall before we do the alignment, we stall before decode, and we have stall at commit. If you're not at one of those points, the instructions are just going to fall down the pipe. We have 2 symmetric execution ALU pipes, so they're exactly the same. We have 4 ALUs I'll talk to in a minute, but they're exactly the same. And in this pipe, if we had 2 instructions, I0 would be the older, I1 would be the younger. Our load store pipe is 3 cycles, so we have a 3-cycle load to use. So if the ALU happens to be in the primary adders, we have a 3-cycle load to use. If the ALU happens to be in the secondary adders, then the load to use could be either 0, 1, or 2 cycles. And basically, the decoder is trying to determine the best latency to schedule down the pipes for that to happen. Our load to use on the load store pipe is 3 cycles. However, we optimized it later in the project. So for pointer chasing, load to store, or load to load, we do it in 2 cycles. So we have a 2-cycle load to use on the load store. Multiply is a 3-cycle pipe, and our divider is a simple 1-bit non-restoring, so we do it out of pipe. Branch handling, branch prediction. We do the standard G-share branch predictor. We use a hash of the global history of the last n branches with the PC, and we use that to look up in a history table. The sizes of our history table are from 32 entries all the way up to 2,048 entries. And then that gives you the direction, but you also need the target. So we have a branch target buffer that we maintain, and we have up from 32 all the way up to 512 entries in the BTB. So all of this is configurable. But what this gives us is it gives us the ability at the front end of the pipe to predict if a branch, if we've seen it before and we know it's taken, then we can go ahead and fetch the target path. And we have a 1-cycle taken branch penalty to do that. In deeper pipes, you need to do that to have good performance. The other 2 things to mention is that if a branch, sometimes your predictor is wrong, it could mispredict. If it mispredicts an E1, we have a 4-cycle mispredict penalty. If you mispredict an E4, it's a 7-cycle penalty. So this is the physical layout of the core. This is just one of the many configurations that are possible. I think the main takeaway here is you remember those main RISC-V components like DEC, LSU, IFU. These are the integer register files, the execution unit, IFU, and the ALUs. About 80% of this layout is due to the RISC-V components, and about 20% is due to bus interface logic, debugger, DMA logic, the programmable interrupt controller, and JTAG, things like that. At SSG corner, at 1 gigahertz, the area of this is about 0.13 millimeters squared. And if you run slower, as it looks like our partners are going to run slower, you're going to be about 0.1 square millimeters. At TT corner, you're 0.1 millimeters or less at all the frequencies, and this runs up to 1.8 gigahertz, although we didn't actually tune it to run up to 1.8 gigahertz. And performance. So actually, this is the start of the out of order cores. These are in order. These three here are in order. These are all out of order, and this one's out of order. So we're an in-order core, and this is core marks per megahertz. So our performance is pretty good. There are other cores out there that have performance but this is about as high as you see on an in-order core. The Rocket, the booms, these are RISC-V. This is RISC-V in order. This is ARM in order, and this is ARM out of order. So on core marks has a bit of a serial content, so it's maybe not the best benchmark for out of order. But the takeaway here is that the performance on this core is quite good for an in-order design. We didn't do anything with the compiler. We didn't change the compiler. That's out of the box using the compiler as is. And these are all single-threaded results. And then our DMIPS per megahertz, we're 2.9 DMIPS per megahertz. That's our score right now. And to do that, we used an optimized string copy function. And that's pretty much it.
All right. So the size of main memory is one of the more powerful drivers of CPU microarchitecture. And today, if you want more main memory, right, you have to buy more CPUs. And you can kind of play that game up to a point, up to about 8 sockets, right, at which point you hit a brick wall. Because there's simply physical limits, right, on how much power and cooling and copper you can pack into a certain size of enclosure. And so beyond that point, you kind of have to go to some sort of fabric. And fabric is perhaps a little unfortunate term because it means different things to different people, right? So today, if you ask a guy to draw you a picture of what a memory fabric looks like, they'll usually come up with something that looks like RDMA. So you essentially go buy an Ethernet NIC or an InfiniBand NIC from Mellanox or Intel. You have some sort of software that manages tables in that NIC to reconcile your local idea of what memory means with the fabric idea of some other guy's virtual memory, right? And then whenever you have a cache miss, it's still served out of DRAM, but you can basically make calls here to map pages from the fabric into your local DRAM and extend the size of the memory that you see. Now, this has become very irksome because of this lightning bolt here. So you basically have a context switch every time a page goes in and out. And the fabrics have gotten so fast that this context switch actually takes more time than the time it takes to go fetch the data from the other side of the fabric. So we are, of course, playing this RDMA world quite a bit, and we decided that this has to go, right? So the next step in this story would be protocols such as Gen Z, where you still keep the software, but you get rid of the context switch, and the idea is that whenever you have a cache miss, you actually go direct into the fabric with a read or write request, right? So this fabric would present itself to you as some kind of a memory fabric where you read and write from. And then you still keep the software to manage your tables that reconcile your local idea of physical memory space with somebody else's idea. But the idea is that you now don't have the context switch, right? You basically stall the pipeline for as long as it takes for this data to come back to you. And this is fine, right? The problem with this is that you have no synchronization, right? So in this story, you have a giant scratch pad that basically has no coherence and you have no consistency model on your memory. So this is not what we mean by this new term omni-extend. So what we omni omni-extend is basically going all the way, which means that your CPU on cache misses goes straight into the fabric. But basically, the fabric would carry traffic that is your coherence traffic, right? So it includes your synchronization, includes your memory consistency model that expands over the size of the entire memory. But now the idea is that this fabric would be something that anybody can buy and extend and scale up. And I've tried to illustrate this, going all the way thing as these page tables here would actually sit on the other side of the network. So you don't necessarily have your local page tables and your local MMU, but rather you have a global address space that's shared between all points. So this is what we call omni-extend, right? So the idea is that Zvonimir showed this idea that you have the cores and you have the encore, and the encore will give you a bunch of interfaces, and we hope that all these interfaces in the RISC-V ecosystem will be fully open and unencumbered. And then you can connect boards one to each other, or you can connect them through some sort of a switch. And so typically within this encore, you'll talk some sort of coherence protocol like TiLink. Of course, it can be any coherence protocol that your caches take, not just TiLink. But then what you put out on this wire is what we call omni-extend. And today, this is just TiLink over Ethernet, right? So we're using Ethernet L1 as the underlying fabric, and then we're sending TiLink traffic over this. And the idea is that you can connect boards directly. And you can see this link today in our booth downstairs. There's a demo on FPGAs. But there are these programmable switches now in the Ethernet world that basically you can remove Ethernet L2 and replace it with your own sort of L2 protocol. And we do exactly that with the tiling protocol. And so we're a storage company. Why do we care? Of course, we want to sell you appliances that basically you plug into, they show up as a giant main memory. So how does it work, right? Like I mentioned, these new Ethernet switches are programmable. The language is called P4. You can either use an FPGA with sort of Xilinx SDNet is one option if you want to play with it, or you can buy a barefoot Tofino switch. Off the shelf, they're at 6.4 terabits per second, and just today there's an announcement of a 12 terabit switch coming out in a few months. So this is your standard Ethernet frame, right? L1 frame, you have preamble, starter frame, and the frame. Instead of using the L2 frame with a MAC source and destination address, you just replace that with a tiling protocol. And that's what the OmniExtend looks like right now. This is all on GitHub. There's a spec there, and there's also bit streams for the VCU 118 FPGA card, so you can download the bit streams and you can play with this. And this is more, how much time do I have? I'm probably out of time. So this is how P4 looks like. So it's a language that kind of sort of looks like a C. And then you basically have these pipelines of match action tables that you're allowed to change packets in your state in the switches. So now we can keep the directory for coherence in the switch and so on. So we're committed to this idea at Western Digital. So we're actually going to be making a platform for this. You see it's organized around an off-the-shelf barefoot Tofino switch, but it looks much more like a motherboard. And the idea is that we standardize these interfaces so you can bring in CPU cards and storage cards and accelerators and plug them all into the same chassis. Or you can just use a top-of-rack switch with cables.